It's all yours. Take it.
Well, thank you very much for the generous introduction and for the kind invitation. I would obviously have loved to come to Cambridge in person, which is, I hear, a beautiful place, even at this time. And it's not only one of the best places in the world to do psychology teaching or training or research, but also in particular a hotspot for comparative psychology. And this is of relevance for my research topic. And I'll be speaking about human behavior under threat and how humans avoid and escape threat. And much of what we know about this obviously comes from animal research. And I will be arguing that this is interesting, that it's relevant, and that it's also challenging, not only for the agents that do these behaviors, but also for us as psychologists to understand it. And I'm happy to take questions during the talk, and I'm going to take my headphones off now. And this means that because my audio is so poor that I would have difficulties understanding you, so there may be a little gap while I plug my earphones back in when you ask the questions. But do please speak out or put them in the chat. Okay, so much of what we know about behavior under threat comes from animals, as I said, and I want to show you a little example of this. This antelope, like so many other mammals, is able to almost immediately initiate a response. When the crocodile lunged out of the water, it jumped, and this is not just a reflex. As you can see, it turns clockwise, such as to avoid the rock wall in the background. And then it lands just at the right angle so as to continue the escape running. And this type of behavior really brings the biomechanics of the body to its limits, and also the neural system that controls it. And although we know much less about human behavior under threat, our preliminary virtual reality research suggests a similar pattern. Here you can see on the right-hand side a participant who tries to avoid a panther. On the left-hand side, you can see what they see in the virtual reality goggles. And as the panther lunges out of the bush, this person jumps backwards, then turns around in order to get into a safe hut, which you can't see because they're not looking at it. And unfortunately, they miss it, and so they will actually get killed in that episode. And at the last moment, the person braces himself to soften the impact of the attacking cat. And just as a footnote on research ethics, we have a high and very strict exclusion criteria to make sure that people with previous trauma history or motor impairment do not take part. And most of our participants find it really fun. I have played the games many times, and although it is a bit scary, I'm particularly scared by the snake. It is also very entertaining. So if you ever want to take part, just sign up as a participant. And so what I want to say is that this behavior is sophisticated and diverse, but current conceptualizations of behavior under threat often just use very simple and coarse categories. And this makes it sound almost as if we only had to select whether we fight, flight, or freeze, and there we go. And as if these were then reflexes or fixed action patterns that just played out. And I want to show that this is perhaps not the case, and much of what we know about this for ethical reasons comes from field observation in animals. And this is from a review that was published by Tiago Branco's group at the Sainsbury Wellcome Center here at UCL, who beautifully collected all the evidence and all the factors that modulate animal behavior under threat. And it is the presence of desirable resources, so mostly food, that can hugely change an animal's escape behavior. It is also the biomechanics, for example, the ongoing own behavior. So the animal will take an escape trajectory or an avoidance response that is particularly suited to its current body position, such as to maximize the success of its responses. It will take into account the threat approach trajectory, and some animals are subject to ballistic predators. For example, birds of prey will at some point get into a ballistic approach, and at that point they can't change paths any longer. And so a prey animal may wait until the predator enters the ballistic phase and then escape. Many animals also learn from past experience very rapidly. They can learn predator and shelter location. They often can even approach the threat in order to find shelter. And they will also learn about the probability of threat and take that into account when planning their behavior. And some animals use unpredictability tactics. For example, they may change their behavior upon repeated threat exposure, and also within one escape response, they may use unpredictable so-called protean behavior. And the classic children book example of this is the hare that escapes in a zigzag. Now, as I said, in humans, we know much less. Our knowledge mainly comes from fiction. I counted over 20 distinct behaviors in Homer's Iliad. But of course, we don't know. Is this diversity just an expression of the fact that the narrators get bored when they use the same words all the time, or the same concepts? Or does that reflect true behavior? Have the narrators actually ever observed warfare, or have they only learned about it secondhand? I think this is often unclear in fiction. And so this is why I'm interested in doing research in human participants with all the ethical constraints that come with it. And I think this kind of research and these types of situations are crucially different from what is standardly investigated in psychology. You might say, well, we know a lot about decisions and how decisions are being made. So what is so different in escape or survival decisions? And I think one of the crucial differences with standard decision experiments is that often there's ample time in value-based or perceptual decision-making experiments. So there is no need to act very quickly. And even if the responses are speeded, even if there are limits to response times, then the execution of the response usually doesn't have an impact on the outcome. So we're dealing with one-shot decisions. You make one choice, and that's it. Whereas if you escape from a threat, then you do this in continuous time. And to model that in the laboratory, at least we need multi-step decisions or even continuous time behavior. And this is not only a limitation in the laboratory, this also reflects the fact that value-based choices are in real life also often without time constraints. Think about consumer choice in a supermarket. Another area of research that is close to ours is movement science. Now, movement science often focuses on movements that can be repeated many times, that can be rehearsed as often as you want. And this is in neurology often gait. This is in sports science, these are particular sports movements, and in psychology, these are often reaching movements. And this is very different from escape responses, which you can't rehearse, at least not in real life many times. Now, interestingly, some of this rehearsable behavior occurs in the opposite situation for the predators. The predators can rehearse their hunting, and humans do that. You can rehearse, you can practice to throw a spear as often as you want. And this is how sports emerged historically. And sports science, of course, has a huge focus on that. But you can rarely practice how to escape the spear. Now you may say, well, children do rough and tumble play, and also many non-human animals do that during their development. And that reflects to some extent of fighting, play fight, and this involves, of course, defensive behavior. And I would like to say that this is true. This is also very interesting because it may be one of the routes how that behavior actually emerges, but it mostly only relates to defense against conspecifics, and also just from informal observation, the actual behaviors that we observe are to some extent different from the behaviors that we observe under real attack from a conspecific. And of course, rough and tumble plays various other roles as well. For example, social bonding or the establishment of hierarchies in a social group in a playful manner. And so this is not always directly related to rehearsing threat escape. And then when this is also complicated, why would we want to investigate it? Why is it relevant? And I just want to speculate a little bit what it could be relevant for. And again, we don't know that much about what humans do under threat. So I did some YouTube research, but this is, of course, not quite the way to go about it. But this is all I can present at the moment. Now, what you can see here are three ladies who, according to the video descriptions, were exposed to tarantulas without knowing what they would expect. And as you can see, they intensely watch the tarantula. This is a video of a lady that sees a tarantula on her sofa. And again, she watches it, she springs up, she also shrieks. I'm not sure if you can hear that. She's a warning signal. And then she moves over to her infant, presumably to protect it. And this is what you could imagine is a normal response to a spider. Now in this video, we see a very different behavior. This is a lady who was quite cruelly filmed by her boyfriend. And according to the video description, this is a lady with spider phobia, and she looks away from the spider. And we know that from clinical observations and also from some eye tracking research that people with spider phobia find it very difficult to watch a spider. But then this may be quite suboptimal if you see a spider in the wild that is truly dangerous. And so one argument is that people with spider phobia avoid looking at the spider because they have spider phobia. But you could also turn that around and say maybe spider phobia is the consequence of not being able to respond properly to a true threat. But this is again speculation, and it's difficult to decide without proper investigation of that. And so this is what we're doing at the moment. And finally, I think this type of behavior is also interesting for computational neuroscience because it poses a number of interesting challenges. To start with, you need to be very fast. So we know that some responses to threats in some mammals take about 5 milliseconds to emerge. This is extremely fast, even for a contemporary computer. You then need to integrate information continuously while you act. This is, of course, true for many motor responses, but here it has a particular relevance. So you need to be very precise in this continuous integration. You need to adapt your goals while you're acting. And finally, learning from errors is often impossible. If you don't manage to escape the spare, then this is the last time you have tried it. And so standard reinforcement learning algorithms may not be applicable here. And of course, in any given situation, the best action is the one that maximizes your utility towards some goal. But this action can be very difficult to compute and is often actually not computable, particularly under these challenges. And so AI research and cognitive science have suggested a number of mechanisms, a number of approximating mechanisms that come close to the best solution. And the crucial feature of many of these mechanisms is that they only really work well in some niche of the environment. They don't work well all over the place. And so what that could mean is that instead of having just one decision-making mechanism in our brain, or two or three, there is a whole bunch of mechanisms, each of which is tuned for particular niches of the environment. And what could these mechanisms look like? These are just simple examples from standard cognitive computational neuroscience research. The most general and optimal mechanism is what we often call goal-directed behavior or model-based instrumental control, where an agent goes through all possible actions, evaluates each possible outcome, and then computes the best action. And you can simplify this algorithm in various different ways. One simplification is that you make it inflexible or implastic. So you remove synaptic plasticity from some of the encoded parameters here. For example, you can hardwire or fix the probabilities. right? And then you cannot learn from experience anymore. You can still go through all the different options and compute the best action, but you cannot change the transition probabilities in this algorithm, and that could be called model-based Pavlovian control. You can also simplify the selection of actions by not considering the outcomes and instead just learning a scalar value for an action. So this is the famous mouse that learns to press a lever to get cheese, and then when it is not wanting cheese anymore because it is hungry, for example, if it is using instrumental control, it will still press the lever because it has learned lever pressing is great. And then it gets the cheese and is disappointed because it's actually not so great. And after a few trials, it would stop. But healthy mice or rats don't do that. They're actually goal-directed. You could also simplify this further by, again, removing the possibility of updating the state values, and that would then become model-free Pavlovian control. And there are, of course, all blends of these algorithms. You could also simplify a decision algorithm in another way or in other ways. One would be to constrain the sensory input that it takes into account. For example, startle responses can only be elicited by particular auditory, visual, or tactile stimuli and not by others. Or these famous experiments by Garcia, who showed that rats can, of course, learn to freeze in anticipation of a foot shock when the CS is audiovisual. But they cannot learn to freeze in anticipation of a foot shock when the CS is a taste. And in reverse of that, they can learn to avoid a sickness US when the CS is taste, but they cannot learn to avoid the sickness US when the CS is audiovisual. And so it seems that these two different learning systems take different sensory input into account. You can also constrain the action menu. You can preclude some actions that the organism can normally take. For example, nose poking is a standard behavior in rodents that they use to look for food. And so obviously it's very easy for them to learn to nose poke when they look for food. And even when they're close to starvation, they may still learn to nose poke and can be trained to nose poke to avoid then starvation in an experimental setting. But when you try to train them to nose poke to avoid a foot shock US, they find this very difficult. So to say, it is not on their mind to nose poke when a foot shock is around. And this is what is meant by constraining the action menu. And so the hypothesis is that there are niches of the environment in which people or animals use different algorithms, and these algorithms have different fingerprints or different characteristics. And the question that we have now is, what are the environmental dimensions that determine which algorithm you use? And there are different theoretical proposals for that. One is that it depends on the type of threat. For example, predatory is threat versus conspecific threat versus inanimate threats. Another is that it depends on whether the response is innate and not so learned in evolutionary time rather than during development versus acquired through learning. Although more recently, I think there is some debate about whether this distinction actually exists and whether the mechanisms that encode these two types of responses are not actually the same. And the third is that these algorithms could depend on how far away the threat is. So it could depend on the physical threat distance or on this concept of defensive distance, which is actually quite ill-defined currently, and we would like to define that better. But to do all of that, to do that research, we first need an experimental platform, an experimental paradigm. And what you see here is obviously not a suitable experiment to do in humans. This is again taken from YouTube. And over the past 15 years, many researchers have resorted to serious computer games. And this is just a quite famous example from my former colleague, Dean Mobbs. When he was at UCL, he's now at Caltech. And many others have used similar abstract computer games. And these are just some examples that are supposed to resemble approach avoidance conflict, which is a rodent anxiety test. And you can see how different they are. And you can also see how abstract they are. There's no actual threat visible. There is no actual behavior. And if the brain truly contains multiple decision-making systems, then yes, perhaps there's one system for serious computer games and another for making actual decisions. And we need to somehow validate that the abstract experimental tasks that we use have anything to do, or that the decision-making mechanisms involved have anything to do with those used in real life. And of course, this is a problem throughout psychology, but it is particularly pronounced here. You can easily imagine that a value-based decision-making task on the screen is much more closely related to consumer choice in a supermarket than these tasks are to the survival choices that we make. And so in this paper here, I've laid out some of the criteria that you could use to validate such tasks. And I've validated three of my own tasks, 3 tasks that I've developed on some dimensions. These are 3 tasks that resemble approach avoidance conflict. Approach avoidance conflict is a situation where animals approach a reward, often a food reward, or explore some spaces under the risk of being predated upon or getting another punishment, another aversive stimulus, such as the elevated plasmase, the open field test, or operant conflict tests. And these 3 experimental setups are supposed to reflect some of this. And the classical findings in rodent approach avoidant conflict tests is that anxiolytics, benzodiazepines, reduce cautious behavior. Anterior hippocampus lesions have the same effect as anxiolytics. And we often see increased activity, in particular theta and also gamma power in oscillations in the anterior hippocampus, which in rodents is the ventral hippocampus. And so for one of these games, I and my team have shown that several anxiolytics reduce cautious behavior. For a second, for 2 games, we have shown that hippocampal lesions reduce cautious behavior. And for all of these, we have shown that anterior hippocampus bold signal co-varies with the threat level, with the threat probability in these games. And for one of them, we have also shown that the power of gamma oscillations in the hippocampus co-varies with the threat level. And this lends at least some credence to the idea that the neural decision-making systems could be similar to those involved in the rodent setups, which involve actual threat. And I'd like to zoom in now on one of these paradigms and quickly run you through it. This is what I call the scoop and run paradigm, because your task is, you're the green triangle, your task is to go out of this safe place, scoop the token when it appears, and run back to the safe place, right? And if you don't do that, then the token disappears after some time. So the trial starts. You can already make a decision what you're going to do, because you know what the gain is. The gain is 1 token, and you also know what the loss is. The loss will be the number of tokens you see down here. And then when the token appears, you implement your decision, and then you go back. So the 3 outcomes are: you approach and collect the token, you approach and get caught, or you avoid, you don't do anything. And what we see is that the more tokens you lose, or the more likely the predator is to wake up, indicated by these 3 colors, the less likely people are to approach and get the token, which is, of course, the reward maximizing behavior. Also, as threat level or loss magnitude increase, people are slower. The latency of the first response, the latency of the approach, gets longer. Whereas for the return to safety, we see the opposite pattern. They are faster when it's more dangerous, which is again reward maximizing behavior. And I'd first like to focus on this reaction time pattern here, because that is not quite optimal behavior. Because when the token appears here at time 0, then the probability of getting caught, the expected loss, is constant over time. But there is a chance that the token will have disappeared when you go, if you wait, because the token disappears with an exponential distribution. So the longer you wait, the more likely that you have missed the token. And because there is a lag between your action initiation and the execution, you may actually go outside of the safe place and have that risk of getting caught and still miss the token. And so the best you can do is to go as quickly as possible. But in real life, threats and rewards are often correlated in space and time. And this has been shown many times on the time scale of hours to days. If you think that this is also true on the time scale of seconds, then the risk of getting caught may be particularly high after the token has appeared, and it may be reduced afterwards. And if that is the case, then there can be a sweet spot where the expected utility is maximized, that is not zero, that is a bit later. And if that is the case, then as a mathematical consequence, this reaction time pattern should arise. Now, this is just a thought experiment. I'm not saying people actually have that model in their minds. I'm just saying if they had that model in their minds, then this is the behavior they should go. But can we somehow infer that they really have that model in their mind? Well, we can try to find a different task where that model leads to a different type of behavior, and we can see whether you can still infer the same model. And that would somehow suggest that this model is truly implemented in their mind or in their brain. And to this end, I designed the safe predator exposure task. After doing the token collection experiment, I gave the same setup. I showed the same graphical setup to participants and asked them to press the key whenever they thought the predator was active. And they were rewarded for making a correct response. And they were also rewarded for making a quick response because the trial ended when they were successful. And there were still tokens appearing, but participants were told they couldn't collect them. And then the null hypothesis is that responses are randomly distributed or uniformly distributed across the trial. And the alternative hypothesis is that they occur more frequently after the tokens. So when we bin the responses with respect to the previously occurring tokens, because the interval between the tokens is variable, this is our null distribution. And this is what people do. So they're much more likely to press the key immediately after a token has appeared than follow the null distribution. And the best fit for this reaction time pattern is a weighted sum of an X-scarce model, which is a simple reaction time model with a null distribution. And you can see that this weighting factor changes from one block of 45 trials to the next. They become more likely to follow the null distribution in the second block, but still, the majority of times they still press after a token appears. And this is some circumstantial evidence, at least, that people really have a particular model that makes them press the key after the token, and that also makes them hesitate while they approach when they're under threat of getting caught. So if that behavior, if that decision to this approach latency decision, if that is model-based and rather than model-free, as I've just suggested, then the next question is it instrumental or is it Pavlovian? Can it change? Can people learn from experience that some of these transition probabilities have changed or are wrong maybe in the first place? And to test that, I designed a different experiment. And the classical way of testing it is shown by this experiment by Hirschberger, where chicken are exposed to food. And if they run away from the food, then they're sitting in a cart, and then the cart will run with them and actually overtake them, and they will get to the food if they run away from the food. Whereas if they move towards the food, then they will not then they will not get the food. And chicken find that quite hard to learn. So their responses seem to be biased in terms of approaching the food, even if that is the wrong thing to do in the experimental setting. And similarly, or actually quite differently in terms of the experimental setup, but similarly in the explanation, Markita Masib showed in this experiment that people find it a lot easier that a go response leads to a win rather than that a no-go response leads to a win, and vice versa for go and no-go responses to avoid losing. So there seem to be some behaviors also in humans which we find hard to learn the experimental statistics about, as if there was something fixing some presupposed probabilities. And so the way I tested that here is that I slightly changed the setup, that people were separated by this black barrier, or the green triangle, the avatar, was separated by a black barrier from the token. And while the black barrier was up, they couldn't be caught. Now, when the black barrier disappears, in this situation, when you have a long approach latency, you will be less likely to get the token, but it doesn't impact whether you get caught or not. You would simply lose the token. Whereas in this situation, if you have a long approach latency, you will be less likely to get the token, but also you will be more likely to get caught. And so the question is, do people learn that, and can they reduce this long approach latency in this situation? And what we see is that their action, so the proportion of approach, is relatively similar, whereas their approach latency is reduced by about 200 milliseconds. And this develops over time from a first block of 45 trials to the second in particular. And this seems to suggest that people start off with a long approach latency and then learn by experience that this is that this leads to unintended outcomes and then changing their behavior. Now, if then the choice between in this situation is model-based and instrumental, then how is that implemented in the brain? And in this task, you actually have only one action that you can do. You can approach, whereas the avoid action is a non-action. You don't do anything. And this action can lead to different outcomes, which are probabilistic. The question is, and somehow these outcomes need to be represented when you make your decision, because in tree search, you need to consider all the outcomes. Now, this is formally similar to the decision between multiple actions, each of which leads to a deterministic outcome. And this situation is actually quite well researched, both in humans and in rodents. And it seems that in this situation, there is a sequential reinstatement of the possible choices, while in this case, animals make a decision, right? So neurons represent the different action outcome pairs in a sequential manner. You can see how they switch from, in this case, a chosen to an unchosen option and back. And also, they're more likely to represent the chosen than the unchosen option during making their choice. And this is also somehow similar or resembles forward sweeps in place cells when animals approach at a choice point in space. And these forward sweeps of the place cells then predict future paths. So the animal is more likely to choose the path that it has swept more often. And so we wanted to know whether there is also a sequential representation of the different outcomes in this situation, where there is only one action, but multiple possible probabilistic outcomes. And this work was done by my former PhD student, Giuseppe Castagnetti, who then did a postdoc at the ICN here at UCL and is now a researcher in the AI industry. So to recap the game structure, you first make a decision at the beginning of the trial, at least this is the assumption. Then when the token appears, you implement that decision. And then you have, when you have two possible actions, the go action, which is approach, and the avoid action, which is a non-action. And for the approach action, you either get the token, which we call P as it's positive, or you get caught, which we call N as it's negative. And so we first focused on the outcome phase. This is the trial start, the choice deliberation phase, the token appearance, the action implementation phase, then you move, and then the outcome occurs. And we tried to find patterns of brain activity using magnetoencephalography that distinguished between approaching and collecting, the P outcome, and approaching and getting caught, the N outcome. And we found that these two situations were optimally classified after 310 milliseconds. Then we optimized the classifier, and the performance is around 70%. And these are the brain patterns at the time of the outcome that distinguish the two different outcomes. And just looking at the source, doing source inversion, looking at the brain areas that generate these responses around this time point, they mostly come from the prefrontal cortex, and it's not. It's a bit more difficult to see also from the visual cortex. And now we took these brain patterns and applied them to the data from the choice deliberation phase, from the decision phase, to see whether the positive or the negative outcome was represented at each point in time. And of course, this will give you a P or an N for each time in that you put into the algorithm. So by itself, this won't tell you whether these are true representations or just noise. So we need to find a method to determine this. And one method is to look at the temporal structure. If you think this is a sequential reinstatement, then you might also think that it has a specific duration. This is at least also what happens in the hippocampus in place cell forward sweeps. And so we tested this, and looking at the autocorrelation in these decoded time series, we find that they are more autocorrelated than chance at shorter lags and less autocorrelated than chance at longer lags. And looking at the duration of uninterrupted P or N epochs, we see that very short epochs below 20 milliseconds are less frequent than expected by chance. Between 20 and 40 or 80 milliseconds, they're equally frequent. And then actually between 40 and 120 milliseconds, they are more frequent than expected by chance. And then they become again less frequent. And so you could say that these epochs have a characteristic duration of between 40 and 120 milliseconds. And same pattern emerges when we look at the transitions between P and N per trial. So it seems that these decoded outcomes have a non-random temporal structure, and that suggests that they might be sequential reinstatements of the two outcomes. And they also depend on the threat magnitude. So at this in this particular time window, but this is of course corrected for multiple comparison across the entire 1500 milliseconds. In this short epoch, in this short time window, you're more likely to represent the positive outcome when the potential loss is smaller. And this is also the case after the token has appeared, immediately before action execution. And at this point in time, there is also a prediction of choice. So you're more likely to represent the positive outcome when you're going to approach the token as opposed to avoid it. And all of this together suggests that these are not just random patterns, that there is a sequential reinstatement of the outcomes during the choice deliberation period. But it doesn't tell us where this comes from, because we have just used a classifier that tells us whether P or N is more likely. But even when there is nothing represented, this would still give us a P or an N. So what happens when we now look at, is P more likely to be represented than just something else? So we trained a classifier of the positive outcome versus null samples drawn from intertrial intervals, and the same for the N outcome. And what we find is an interesting asymmetry. We find that during this time window, the difference between or the impact of threat magnitude is actually due to a more pronounced representation of P, whereas the representation of N is unaffected. Whereas immediately before the action, the relationship with threat magnitude and with choice are due to a less pronounced representation of N. And so it seems that the reinstatement of the positive and the negative outcomes also may have a different function at different phases of the choice period. So to summarize this part of my talk, model-based choice under threat may be supported by tree search, at least for shallow trees, because these were all one-shot decisions. Although they were implemented in continuous time, you only had to optimize the action execution in terms of an approach latency. And it seems that individual probabilistic outcomes are reinstated sequentially during this choice period. Simultaneous reinstatement would also be possible, but it's not what we see here. And from a theoretical angle, simultaneous reinstatement doesn't scale very well with large outcome spaces. The reinstatement strength relates to choice. And the question is now, this is a very artificial lab task where you respond on a keypad. So how does that generalize to embodied choices? What if people, run away from a crocodile? What happens then? And when they when they use their full body to make a response, and also when they operate in space. And an interesting question would be whether hippocampal replay may be a mechanism by which the possible options are reinstated. Now, the problem with reinstatement and the problem with model-based research in general is that it doesn't scale. So it is quite nice if you have 2 outcomes or 4 or maybe 10 outcomes, but if you have multiple sequential actions, it becomes very cumbersome. And basically nobody can do it. If it gets too large, then even contemporary computers can't do it. And so surely this is not how AI algorithms learn to play Go or chess. So maybe there are other ways that the brain can, or that the mind can implement such decisions. And to test that, we removed the continuous time component and devised a sequential decision-making task. And that work was done by my former postdoc, Christoph Korn, who is now a professor at the University of Heidelberg in Germany. So the task is that you're for 5 days in a forest. And on each day, you decide whether you want to wait or to forage for food. If you wait, you just lose some energy. You burn some calories just, due to the passage of time. When you forage, you also burn some food, and you burn some more food, some more calories, because you spend energy on foraging. But you may also be lucky and get food. So then you increase your calorie reserve, and the internal energy level is depicted on each trial. And if that hits 0, then you starve. Okay, so on each trial, you need to make that decision, and you also need to take into account that you will have to make that decision in the future without knowing whether you'll hit a good or a bad day in the future. In each forest, there are 2 weather types, and these different weather types and the different energy levels were designed so as to maximize the variability in people's behavior. And in a second version of the game, there was also a predator present in the environment, and the probability of the predator hitting you is depicted by the size of this lion icon, and if it hits you, then you die immediately. Now, you could say this is rather more abstract than the previous game, and is even further removed from embodied behavior, from embodied choice. And just to show that people really care about starving, Christoph did a pilot study. In this pilot study, he gave people lotteries. These are standard economic lotteries, and he told them they have to decide between this lottery of gaining nothing for that probability and gaining 2 points with that probability, or 0 and 3. And these lotteries would be played out 3 times in a row. And if their energy levels hit 0 at any point, they would starve. Now, the utility maximizing way of doing that is to work out all the options after the 3rd day, and you can then depict that as another lottery and just make an economic choice between these 2 lotteries. And this is not what people do, apparently. So when they see the foraging frame, the best model, or the model that best explains the data, is a model that uses the expected value of all these options together with the probability of starvation. So people try to maximize expected value, but they also try to minimize starvation. And interestingly, in a second task that either preceded or followed the foraging task, Christoph gave people exactly these these lotteries that result from those, and people behaved in exactly the same way. So they predominantly or they jointly maximized the expected value, but also minimized the probability of getting nothing out of this. So there seems to be something special about this 0 outcome. But in any case, it seems that people understand this, and they don't like to starve in this environment. So this convinced us that we can use that to look at actual behavior in this, to reflect actual starvation avoidance. Now, this game that Christoph devised has a closed form optimal policy, and it's, with paper and pencil, it's quite easy to work out. But it's not easy from the top of your head. So I have a math degree, but I couldn't do it in my head. So I need to sit down and write it down, and then I can work it out. And the question is then, do people use this closed form optimal policy, or do they use something else? And they could also use various heuristics in this game. And so Christoph first simulated different possible heuristics that you could use. And this is just a list of some of them. And the deterministic optimal policies, of course, optimal in terms of avoiding starvation. This is why it's the optimal policy. And the next best thing is to just look at the foraging success. So in this plot here, you would just look at, on each day, you would just look at how many blue dots are there and go by this. And for the predator game, if there is a predator in that game, then the best thing to do after the optimal policy is to just look at the probability of the predator and only go by that. This is the second best thing to do after the optimal policy. What do people do? Well, we first used a logistic regression with just one predictor, and the best explanation of people's behavior, of people's choices, was just the best heuristic, the probability of foraging success. And in these posterior predictive checks, you can see that this explains the data quite well, although not all of the data. And so we were wondering what explains these remaining, what explains this remaining variance. If we now plug a second regressor into the model, then the best regressor we could plug in is the optimal policy. And that explains the data almost perfectly. So it seems that people predominantly use the foraging probability to make their choices and sometimes use the optimal policy. Could be that these are different participants. Some are maybe more clever than others, or some are more tired than others, or people may be sometimes tired of computing the optimal policy. But it could also be that they compute both on the same trials and then use another strategy to decide between the two. And so we looked at the discrepancy between these two. Most of the time, they will actually make the same prediction. Both will tell you to wait or to forage, but sometimes they make different predictions. And Christoph used the decision variable and mapped and related the difference in the two decision variables to the reaction times. And he found that when the discrepancy is low, the reaction is faster than when the discrepancy is high. And this makes sense because it's more difficult if you have to, or this is an indication that people could have computed both on the same trials, and then it is more difficult to decide. And that would then explain your longer reaction times. And another indication that they really compute both on the same trials is that the difference in decision variables also is reflected in bold signal in the anterior cingulate cortex. But this is, of course, an indirect inference, and we don't know which algorithm would be used to decide between these two if they are computed on the same trial. Now, looking at the predator game, the best available heuristic is the probability of the predator. Again, that best explains the data, and the next, or the best second predictor of behavior is the optimal policy, and again, that explains choices quite well. And this plot just to show that the probability of the predator also relates to bold signal in the anterior hippocampus, which was part of the validation of this game. And again, the discrepancy in the decision variable between these two policies relates to reaction times, although I can't show a plot here. So to summarize, in longer horizon choices under threats, humans use goal-directed decision-making only some of the time. And actually, most of the decisions are based on simple heuristics, but relatively powerful ones. So the most powerful ones in the given task. And it seemed that heuristics and optimal policy were at least sometimes computed on the same trials. And this raises all sorts of interesting questions. For example, meta control, or as in this famous paper by Peter Dayan, who sets the switches on this thing? Is there a homunculus in the brain? Of course there isn't. So there must be some way how these two policies are being arbitrated. And there are several theoretical ideas how that could play out. For example, it could be that the less imprecise prediction or prescription wins. It could also be that the more complicated policy is really only computed when the less complicated one isn't sufficiently accurate. It could also be that there are other algorithms that decide between these, and it could be that it's actually not two policies, but really what looks like a mixed strategy is a particular choice algorithm that we haven't included in our model space. And there are some examples of this, for example, the successor representation, which looks like or can look like a mix between model-based and model-free strategies. And in this paper from University of Zurich, they showed that mixed strategies or what looks like a mixture of strategies in the two-step task can really be explained by participants not learning the task instructions properly. So this is a more trivial explanation and something that we should be aware of. And of course, yet another possibility is that the artificial lab setup, this abstract way of representing a real-life environment, that this does not fit into any pre-programmed decision algorithm. And this is why we observe this mixture, whereas if we put people into the actual environment, they might quite easily choose one algorithm to go with. And so this is why we are now doing virtual reality research, in order to be better able to delineate which needs of the environment use which algorithmic controllers. With that, I'm at the end of my talk. I'd like to thank my lab team at the University of Zurich, who did most of the work. My lab team now at UCL, who is involved in who started the virtual reality work. My collaborators at the various institutions who helped me do this, the European Research Council, who's funding my current research, the Wellcome Trust, the Swiss National Science Foundation, and the Swiss Academy of Medical Sciences. And thank you for your attention.
Thank you very much, Dominik, for a fantastic tour de force. Such impressive and interesting tasks to operationalize complex life situations. I'll stop the recording now.